Now, there has started to be development of resistance to artemisinin or its derivatives. And there's a lot of what we see as partial resistance. So if it's used in a combination therapy, the parasite is not resistant to the second drug. So we use it as a combination. We use two drugs. It still can be killed by the second drug. It just takes longer. And this type of resistance is found a lot in Southeast Asia now. And it's occurred because of poor treatment practices, inadequate patient adherence to the regimes that might take 10 days to get through the treatment. Same as here in the United States when people don't necessarily take their antibiotics for the full 10 days. It's the same exact idea if you don't take your drugs for the full course of the drug treatment, the parasite can grow back even more worse but resistant to the drug. And the use of monotherapy. So in the beginning, artemisinin was used alone, and now we're really realizing we need to use it in combination. So what we're doing now in the last decade or so is learning much more about how this artemisinin kills the parasite and where resistance is arising. And this is really important because remember that the form of the disease in Africa is much more severe and much more deadly. So far, there's very little resistance in Africa, and people are really hoping to keep it that way because if we lose artemisinin drugs in Africa, then malaria will become a much worse disease again. Okay, so this was from a review published in 2015. So if you ask what was the mechanism of action of artemisinin, back when Tu Yu was first doing her work, nobody knew. And it was only really actually pretty recently that we started getting clues about what artemisinin was doing. So the state of the art in 2015 was that what we thought was that the parasite would produce heme molecules, and so would the red blood cell. So notice here that this pink is the erythrocyte of the red blood cell, the white is the plasmodium. So this is the plasmodium pathogen inside the vacuole of the red blood cell. And the hemoglobin, that's the oxygen carrier, could come from this red blood cell into the plasmodium, and then as that was broken down, it would release heme. Now, notice this is the British spelling. This was in Nature Communications. This is a British journal, and they spell heme H-A-E-M. We spell it H-E-M-E. So I just want to point that out. This is the heme that you know about. It's just spelled different. Now, this heme, together with artemisinin, will activate artemisinin. Artemisinin then can bind to all kinds of different proteins. All these orange proteins here are proteins that are binding to artemisinin and being damaged by it. So in 2015, we thought the reason that artemisinin would kill these parasites is it would damage a whole bunch of different kinds of proteins that it could bind to. So not just one, but a whole bunch. Now, we still think that's part of it, but we can add on to that story about why this is deadly to the cells. And that's the paper you're going to read for this week. Now, when there's a lot of damaged proteins, this causes an ER stress pathway. And ER stress activates a whole unfolded protein response, or UPR. And as part of this, there's 3 different subpathways that get activated, and we're going to be looking at this PERK one in specific. And this is going to control the rate of translation. And so when PERK pathway is activated, it turns down translation so that there's decreased proteins that need to be folded up. So we're just going to decrease the demand on the cell. That hopefully gives the time for ER and the protein folding mechanisms to fix all these extra proteins that are misfolded and get us back to homeostasis. This clock is sort of a time. If we can't fix it fast enough, the cell goes through apoptosis. Now, how does that relate to our artemisinin? So here's those 3 pathways looking a little bit closer. I really want to focus on this one here, this PERK pathway. And in the paper that you're going to read, one of the things you're going to look at is this kinase PK4. That's this protein here. This PK4 is going to phosphorylate EIF2 alpha, and EIF2 alpha is a translation factor. When this is phosphorylated, it turns down translation. So we have reduced amount of proteins that need to be folded. And then hopefully those proteins fold, and if they can't, then we lead to apoptosis and cell death. So this pathway is something that's going to be activated by our artemisinin. Okay, so this is from the paper you're reading then. This is their model. So we have protein synthesis, and these proteins have to fold. Artemisinin is going to damage these proteins and lead to unfolded proteins. That was what we showed from the 2015 article looking at heme. So these get misfolded, And then we somehow have to do something with that. So one of the things that cells can do is just decide to degrade all those proteins. Here is our ubiquitin machinery we just talked about in week 1, and E1, E2, and E3. And there's this protein called CALCH that's an adapter that helps take these ubiquitin machinery proteins and lead to our unfolded proteins being ubiquitinated and then degraded by the proteasome. And if that all works great, then we've gotten rid of the problem. Now, what artemisinin does, and what this paper shows, is that artemisinin can increase the amount of these misfolded proteins. It then can block the proteasome. And so we build up all these ubiquitinated proteins that we can't get rid of. That's unresolved ER stress, and the cell dies. The other really interesting thing that we know is that if we go back to that idea of resistance, this CALCH protein is the most commonly mutated protein in resistant parasite strains. And so this is blocking the ability of the parasite to ubiquitinate those misfolded proteins. If you don't ubiquitinate them, they don't build up, and you don't get as much cell death from the artemisinin. And so that's where we think a lot of the resistance is coming from. Okay, so this is just a little background on that paper. Please let me know if you have questions about the paper as you start to read it. Now, the future of malaria treatment is that we are still looking and using these artemisinin derivatives as kind of our treatment of choice in combination with other drugs. We're still working on making them even better. We're really working to try and lessen the spread of this resistance. And we're continuing to use all those other methods to decrease the mosquito population or their opportunity to bite people. Again, bringing in nets that can be given to people in places where they may not have access to that. There is a vaccine that just started larger trials in April 2019 in different African communities. It's not a great vaccine, but it did reduce the number of cases in children by about 36%. And so this is just kind of going into its first big clinical trials right now. Okay, let me know if you have any questions.